Okay, we have a second video on composition of linear transformation in matrices. A little bit of variety here. First, the Kronecker delta function. You may have seen this before. Delta of ij is defined to be 1 if I equals j, and 0 if I is not equal to j. So Kronecker delta of 1, 2 is 0. Kronecker delta of 2, 2 is 1, right? And so, incidentally, the identity matrix, In, can be defined by the ith, jth entry is just Kronecker delta ij, right? 1's on the diagonal, 0's off the diagonals. A few other properties of matrices. Here we have A an M by N matrix, B and C N by P matrices. What does that allow us to do? That allows us to multiply N times B or C, right? Because this has N many columns, this has N many rows. So if we had 1, 2, 3 columns here, we'd have 1, 2, 3 rows here, and it would make sense to multiply. And then we have D and E, which is Q by M. What does Q by M allow us to do? It allows us to multiply on the left. So if A had M many columns, if M had N many rows, so 1, 2, 3, 4, A has 4 rows, D has that many columns, 1, 2, 3, 4, which makes matrix multiplication there possible. So just with that context, A times B plus C is equal to AB plus AC. Matrices work well together. You can distribute from on the right also. This is not correct. This should be EA, right? DA, EA. Then C distributed to two matrices is the same as C distributed to the first and multiplied, or C distributed to the second and multiplied. The identity matrix can multiply on the right and doesn't do anything, or on the left and doesn't do anything, but it's a different identity matrix depending on the dimensions. And finally, if V has dimension n and there's an ordered basis, any ordered basis beta, the identity map on V is just represented by the identity matrix. All of these are quite straightforward. I was thinking we might prove A just as a sense of what's happening here. Okay, so how would you verify something like that? Well, matrix multiplication, usually the way you verify something like that is you say, what is the ijth entry? And if all entries are the same, then you know the two matrices are the same, right? So what's the ijth entry of this? And the ijth entry of this product is equal to the sum k equal, let's see, 1. We're going to multiply across all of the columns of A, n, or the rows of B plus C, that's n, A, I, K, times B plus C, K, J, right? Well, what is that? That's just an element of the field times an element of the field that is the sum of those two. And of course, what's the sum of those? What's the definition of addition in matrix multiplication? Well, that's BKJ plus CKJ, right? And then these are 3 elements of the field, so we can use distributivity to get A, I, K, B, K, J plus A, I, K, C, K, J. But of course, what's this? This sum can be distributed. A, I, K, B, K, J plus the sum K 1 to N of what is this? A, I, K, C, K, J. I lost my train of thought. So what is this? This is the matrix multiplication of A and B. It's the ijth entry of that. And this is the ijth entry of AC. And so altogether, it's the ijth entry of AB plus AC. And that shows that these matrices are equal. Okay, and the last big theorem we'll show, we have used this fact so many times, mainly in 2.2, that the matrix representation of the linear transformation of T going from basis beta to gamma times the representation of vector U in terms of beta, which is an ordered basis of V, equals the representation of the vector Tu in W in terms of the basis gamma. So that's actually equal. And I like this proof. This proof has a sort of a cool approach, okay? So we're going to fix U, okay? So fix some U. It's not going to, we're not going to think of it as moving. And then I'm going to define two maps that you might not expect. I'm going to define a map from the field to V, and I'm going to let it be f of A equals A times U. Well, that's clearly linear, right? As this scales up, any non-zero element A is a basis of f, so that's linear. And then I'm going to define G from F to W by G of A equals A times T of U. Again, it's linear. Same rationale. Now, what I'm going to do is I'm going to start leaning on this theorem we talked about in the last video. Do you remember how we had that the matrix representation of two linear transformations composed to a new matrix representation, right? This is different. This isn't in the definition, sorry, in the theorem itself. This isn't a linear transformation. This is the representation of an element here. But what this allows me to do is it allows me to treat this element like a map itself, okay? So we'll let alpha this be an ordered basis of f, okay? One is an ordered basis of the field, right? And let's just notice that G equals TF, right? So let's think about that. If you took an element from F and you plugged it into F, you'd get AU, right? And what's T of AU? By linearity, T of AU is A times TU, right? So by the theorem, we get the matrix representation of G going from what's the basis of G's domain? Alpha to gamma equals the matrix representation of T, that's going from beta to gamma, and the matrix representation of F going from alpha, that's the domain, the basis of the domain, to beta, right? But note, U represented, the element U represented in the basis beta is actually truly equal to the matrix representation of linear transformation F going from alpha to beta, right? What are those? Well, since both are n by 1 matrices, I mean, we've talked about this being a vector, but a vector is technically an n×1 matrix, right? With coefficients, the coefficients of u in terms of the basis beta, right? Well, that's what the representation of u in terms of beta is. Coefficients of u, in terms of beta, basis beta. But that's what this is also, right? What comes out here for 1 is the representation of 1 in terms, which is f of 1, which is u, in terms of the basis beta. Similarly, we're playing exactly the same game on the other side. T of u, that's an element of the codomain, w, representing that in terms of gamma, is really the same as the matrix representation from alpha to gamma of G. Therefore, what do we get if we had that? And on the left, we can say the representation of that vector equals the matrix representation of T from beta to gamma. And then what's F from alpha to beta? That's the representation of U in terms of beta. So I like this because essentially we get a result about particular vectors by picking simple linear transformations and saying they're really the same thing.